So continuing on from our previous video that talked a little bit about how we saw that we had sinusoidal motion. In other words, we can describe the motion of the position of something in simple harmonic motion with a sine or cosine function. So here we have a function that is the standard for the equation of position of an object undergoing simple harmonic motion. So in this, what we have is x, the position, x max, the maximum position, otherwise known as amplitude, and then we have cosine, the function. Omega here is our angular frequency. And you might be saying, I'm not sure what that means. Angular frequency is going to be similar to the concept of angular velocity, which we already studied, and its units are going to be in radians per second. So angular frequency basically is just going to be 2 pi times the frequency. So that you already know. Then we have the angular frequency is multiplied by time, of course, because it's a position as a function of time equation. And then we have this phi, which is really called a phase angle. And you might be like, I don't even understand what phase angle means. And the phase angle is really more like the fudge factor. This is the term that we put into our value here, okay, that if the time is equal to 0, okay, and remember, cosine of 0 is 1. So let's say that we want it to actually start at the equilibrium position instead of at the maximum position, or maybe it's in the minimum position. So that would be a situation where we want it to start someplace other than where cosine 0 would be. We can add in a phase angle, which allows us to make that work. Okay, so let me get rid of all this so you can still see the basic equation. Then, of course, as you know, if you want to find the velocity of something, you need to take the derivative of the position with respect to time. And so when we do that, we will get that we carry down the x max. The derivative of the cosine of something is the negative sign of that quantity. So negative sine omega t plus the phase angle, and then multiply by the derivative of the function with respect to time, which would just be omega. In other words, the velocity for simple harmonic motion is going to follow the pattern of negative x max omega sine of the quantity omega t plus the phase angle. And then we get to, of course, our favorite, acceleration. And if we're looking for acceleration, we know by definition it's the derivative of velocity with respect to time, or the second derivative of position with respect to time. So for our purposes, that means that what we would end up with is a negative omega squared x max times the cosine of our original function of omega t plus the phase angle. And this should look kind of familiar to you. Didn't we say we've got that the position is basically x max times the cosine of omega t? Don't we have that here? So we can simplify this like a whole bunch and say that A is just negative omega squared times the position. And this, my friends, this right here, this relationship is what makes it simple harmonic motion. So whenever we're talking about simple harmonic motion, you're going to see us deriving an acceleration is equal to like a negative constant times a position value. And getting our angular frequency back in here, angular frequency, as I mentioned before, would just be 2 pi times the frequency, which makes it 2 pi over the period.